Okay, back by popular horror. We have this video just to quickly explain how to answer some of these lithosphere questions and also some of the Earth structure ones as well. So, first things first, I apologise, I've stolen this back from Joe, who decided to have several copies of this, and so a couple of his numbers are on here, they're not right. So what we need to do first of all is we need to measure the continental lithosphere at its maximum thickness. Now its maximum thickness is between where X is down to here. This is all continental lithosphere, they've pointed it out to you clearly here. So we need to measure between X and this base here, and we'll accept anything between 136 and 144 kilometres. Okay, you need to use the scale on the side here and then do some measurements nice and precisely. Then it says state the percentage increase in thickness of the continental lithosphere beneath location X and use the formula below. So our present day thickness at X, well we've just said it's 140 kilometres, minus original thickness, we can just measure that here, 100 kilometres, divided by our original thickness. So we're looking at 140 minus 100 divided by 100 times 100, and that equals around about 44%. So anything between 38 and 50% we will give you. Then state the type of boundary we have here, convergent, divergent or constructive, and this is a convergent plate boundary. They're converging towards each other, so plates move towards each other. There is collision. Any of those will get you those 2 marks. Now this one, never done this before, just wanted to see whether you'd actually be able to look this up. State which type of fault, normal, reverse, thrust or strike slip is shown you in the picture. Well, it is actually a thrust fault because it is low angle. And basically the hanging wall has moved up, but I don't expect you to know that one. However, it's a thrust fault because it's low angle. These here are low angle faults. So they are thrust. If you did look them up online, these words, you would be able to find the answers. So well done to those who did. Now explain why neither of the plates is subducting at this orogenic belt. I think you need to say about 4 words here. Plates have an equal density, both continental, they have a low density would be enough. Also, you could say the plates are too thick. It's very difficult to get 100 kilometres worth of material to subduct. Right, then we have this diagram. Draw an arrow in both of the boxes to say which way these are moving. Now you have a ridge here, and the only time you have a ridge is when you are in the mid-ocean, okay, a mid-ocean ridge. So what we're expecting here is the arrows to line up with what's going on, so roughly like that. So a southwest and a northeast direction. Then, associated with each of the plate boundaries, X, Y and Z, the Earth structure has been raised to form areas significantly higher than the regions surrounding them. State which one of the plate boundaries, X, Y or Z, is most likely to form the orogenic belt. Well, we know that we have the Himalayas here, so it's Y. And the reason for this is because we've got 2 continental lithospheres that are colliding. We have reference to the Himalayas here would be a good idea. So actually say mountains are being built. We have an orogenic belt. Orogenesis is occurring. You could even start to argue it's not X because X is a divergent plate boundary. X has 2 oceanic crusts. You could even say it's not Z because again we have subduction because we have a trench. But you can quite easily get the marks just by pointing out to Y as well on its own. Right, so next one, I believe we've got more arrows to draw. So the Eurasian plate is moving this way, and the Pacific plate is moving this way. Okay, and that's to indicate which direction we have the actual plate subducting. Those arrows indicate to you they're subducting that way, and again the key there is telling us we have a trench. Right, now we need to state which plate boundary we have. We have 2 plates moving towards each other, so it must be convergent. Now we've got 3 marks up for grabs here. Describe the pattern of earthquake foci shown in figure 3b. So we've got a line here. So they increase with depth. So we actually have an increase in depth from your east to your west. We can mention that. Also, we've got 2 lines of them. It's totally fine to mention those as well. They slope at an angle to the west. That's absolutely fine as well to say. Or they're mainly shallower along the volcanic region, and then you have slightly deeper ones around the trench, if you make that distinction as well. You can mention the fact that we have a cluster of shallow focus ones around the volcanic region or under Japan. That's absolutely fine. And you can also mention the fact that they pretty much stop around before the 250 kilometers, but they do decrease as you move into the actual as you move into the mantle. You can mention the fact you've got a series of different clusters. So you've got your trench cluster there and your volcanic region there. And you can also talk about the fact that you have a higher concentration between about 25 and 75 in the trench area. This is all about describing what you can see, so there are several marks up for grabs there. Right, state and explain 2 reasons for the occurrence and distribution of the earthquakes in figure 3b. So we've got 2 separate clusters that are particularly important. So, this one here along the trench, we can talk about the fact that it's a subduction zone and the fact that you're following the Benioff zone. The fact that this is the line at which the 2 plates are moving against each other. You can talk about the friction that's building up between the 2 plates, and the earthquakes are then caused by the release of the pressure. Then with our volcanic region, we need to talk about the rising magma. This causes the plates to fracture, so the magma as it moves up and through the actual surface starts to cause these fractures, and that causes the earthquakes. Okay, magma generated beneath the Japanese islands is andesitic in composition, and we need to explain why it's andesitic. So, we have partial melting of a basaltic plate, therefore it's partially molten, which means the mafic material is now being created into an andesitic version. So you just need to mention the partial melting of your basalt oceanic lithosphere, and that will get you the 2 marks. Now, quite a few people got this one actually, I was quite impressed. Explain why andesitic magma results in more explosive volcanic eruptions than basaltic ones. So andesitic has a higher silica content, or it's more viscous, or you could even say it's sticky. And as a result, the gases can't escape, which means the pressure builds up and it's more explosive. So basically, andesitic is more viscous and therefore gases can't escape. Okay, and then I gave you one that's back to the Earth structure, and you've got a selection of different diagrams here. Now, this seemed to cause problems, and I think it's because you weren't reading your diagrams properly. So the first thing it wants us to do is to read the arrival time at seismic recorder A. So we need to reference figure 2A here, and it's telling us recorder A on figure 2A, it's kind of difficult to say, is at 3,300 kilometers. So again, you're going to need your rulers for this, but I'm going to freestyle it. Recorder A is here, and we need to measure across. And so it turns out it's around about there, so it's about 15.5 minutes, and we'd accept anything between 15 and 16. So then we need to do the old velocity thing here. So it says in kilometers per minute, so we don't have to do anything, just 3,300 divided by 15.5, and then that will give us the, I think it's 212.9 or something daft like that. So 213 kilometers per minute. Then, with reference to figure 2b and your knowledge, explain why S waves arriving at seismic recorder B have a higher mean velocity than S waves arriving at seismic recorder A. So, if we look here, to go into B, they have to travel deeper into the Earth. So they pass more rigid material. As an increase in rigidity, they will move faster. And it's as simple as that. So they will have a higher mean velocity because they are moving into more rigid material. Density has nothing to do with this. Please do not talk about density. It's an S wave, so incompressibility is not important. Right, using figure 2a and the arrival time for the S wave shown in figure 2c, determine the distance of seismic recorder C from the epicenter and show your working. So we can see from seismic recorder C, so figure 2c here, so this is this one, that we are talking about arrival time here is about 17 minutes. So if the arrival time is 17 minutes, trying to get stuck there. We then can go to our graph here, and we need to head up to 17, and then we can read off how far away we are, and it works out at about 5,600 kilometers. We just need to read across. So from the 17 up, and then read across. Please make sure you use a ruler. Then, to show you working out, you just need to put on there that it's 17 minutes and that you read off the diagram. With reference to the seismogram shown in figure 2c, draw in figure 2a a travel time curve for P waves. So with reference to the figure 2c, we need to draw on figure 2a. So if we look at figure 2c, we can see that P waves arrive at around about the, let's call it 8-minute mark. So if they arrive at 8-minute mark, we know roughly they're going to be moving at about double the speed. So we need a curve that's half the time. So it should always start at 0, and that's where the first mark comes in. We need to draw a curve that's this side, and I've got to be honest, I would make sure that it's just a nice simple curve. So start at 0 here. I'm drawing this freestyle, so there's a lot of pressure, and it needs to increase roughly like that. That would get you 3 marks. You can be more precise, but they're not looking for it, to be honest. They are looking to see that you can draw it to make it clear what happens. Approximately half the time of an S wave, so maybe you need to be a little bit closer to there, but that would be absolutely fine, and you need to draw it from the origin. Right, so we've got that side done. Now, seismic recorder D, shown in figure 2b, is 160 degrees from the epicenter, so immediately you should remember there is something about that area that is quite important. So we need to describe 3 differences between the seismogram for recorder C and for recorder D, just 3 differences. So, looking at this, 3 differences. There is no S wave on figure 2D, so that's difference 1. The time between P and S wave is far greater, difference 2. You can also talk about the fact that there's a longer arrival time for specific waves, so P waves arrive a lot later on figure 2D, or surface waves arrive a lot later on figure 2D. You can also mention the fact that the amplitude is smaller on this one. They are far greater here. So any of those will get marks. Right, so we've explained our 3 differences. Again, just reading off the graph. Now we need to use our knowledge to explain these differences between the 2 seismograms. So, figure 2, seismic recorder D, so figure 2D, is further away from the epicenter, which means they have travelled further, therefore their arrival time is greater. We can also talk about the fact that P waves have been delayed by moving through the outer core. Their velocity will be reduced because they've had to move through a liquid which has slowed them down. We can talk about the fact that there's no S wave at D because it's in the shadow zone, and as it's in the shadow zone we cannot see the actual S wave because of the outer core being liquid, and S waves cannot travel through a liquid. So there's lots you can say about that because of being in that 160 degree point. Okay, so that's how you answer those questions, and you can see there's a lot of key terms you need to make sure you understand. If you're not sure, come and ask me, but at this point you should be beginning to get to grips with the words. So if you're not sure, make sure that you have asked me if there's any problems.